Hi, this is Ann Vincenti. I head up marketing for Emu, and I'm here with Eric Hein, one of our engineers who has been doing a lot of work to visualize and improve performance. So I'm going to ask Eric if he can share what he is releasing in this most recent release.
Yeah, sure thing. Thanks, Ann. So what I have here is I've taken, there's a lot of output that you get from the Emu simulator and a lot of data there, and it's kind of hard to look at it all at the same time. So what I've done is written some scripts to run a benchmark and then take all that output and visualize it so that you can see what's going on and debug performance issues. So I'll give you a quick demo here and then sort of talk through the different ways you can use this information. The Emu Sim profile script will be available in the next release. This is a wrapper for the Emu simulator. It takes, the first argument is a folder where you want the output for the simulation to go. And then after that, you can just put a regular command line. So this is my executable, and then here are my arguments. So I'm just going to do, for my first demonstration, a recursive spawn with 256 threads on one nodelet and process 2 to the 12 array. So I'll run that. You can see it's generating the profile in this directory. This is the standard out from our program. Give that a minute to finish here. Usually with the simulator, you'll want to keep the input size rather small so that you can get outputs right away. But you can certainly fire these off and let it finish overnight. So once that's done, I'll switch to the output that I've gotten over here. It will generate a HTML file that has a bunch of different images and reports embedded in it. So this first output is the number of active threads on each nodelet over time. And since this one was a local spawn, we're just going to see everything is on one nodelet here. So this teal color shows the number of threads on one nodelet. Let's see, for some reason this is only getting up to 60 threads. I think that's the grain size that's kicking in there. Right, so when it finishes, you'll see the output. It generates a bunch of pictures, and then this name right here, this is the name of the HTML file to open. So you can see that matches what I've opened here. I actually like to use xdg open to just pass the name of that report. So there you go. So this first plot is showing us the number of threads that were active over time. When you see areas like this where there is only one thread active, that's serial code, so maybe a opportunity to parallelize things. This next pie chart shows you the number of instructions executed per function. So this is like a profiler for identifying which functions are taking the most time. So in this case, the recursive spawn add is doing most of the work. And because this is a small benchmark, malloc and free are actually taking a fair amount of time. For these next functions, I'm going to switch to a little bit larger benchmark. So this is one that I ran earlier that is doing a BFS over a scale, let's see, it's a scale 10 graph. So now we can see the different colors indicate how many threads were active on each nodelet. So this pillar here is saying that we did a spawn, and we see that threads are nice and evenly distributed across all the nodelets. And the pie chart is showing us again that this mark neighbor spawner function is doing most of the work. Malloc and free are still taking a little bit of time. Lots of other good information here. This is a remote write traffic map and a remote atomics traffic map. So in this benchmark, I'm doing a lot of remote atomics. So you can see the source nodelet and target nodelet. In this one, it's relatively evenly distributed. When I switch to this is the same benchmark, but with more of a bad data distribution. So now we see there are these hotspots here. Things going back and forth between nodelet 0 indicates that there's too much data on nodelet 0 and it needs to be distributed better. This next chart is the number of total migrations grouped by function. So whereas the previous pie chart was which functions are doing most of the work, this one tells you which ones are doing most of the migrations. So this BFS2 run and 1D apply are doing most of the migration here. Below this, we see the actual number of migrations. And this one's still a little bit raw and hard to look at, but if you're willing to dig into the assembly, you can see the address of each instruction that does a migration, and then for each function, which instructions it had migrated. We don't have full debug symbol support yet, but like I said, if you're willing to dig into the assembly, you can get an idea of where those migrations are happening. And in this case, there's a relatively small number, so this is pretty normal. If you see something in the thousands or the tens of thousands in here, that's definitely a candidate for a function where you'd like to look for some data that should be replicated. All right, so that's what I have to show here. Again, this is a wrapper script that you can run that'll be in the next release. Do you have any questions, Anne?
You know, I'm curious, Eric, when do you think you would advise someone to use this tool?
Yeah, that's a good question. So there's sort of a strategy right now in terms of performance tuning, because the hardware will give you the fastest execution time, and you can scale up to large inputs and you can get results back quickly. But the hardware doesn't give you a lot of information about what's going on and about what's taking the most time. So I would recommend the simulator here. Once you have a version of your code that is working, but it has some performance problems and you're not sure why, then would be a good time to identify an input set that finishes relatively quickly in the simulator, and then run it through this profile tool and get the set of results so that you can, you know, drill down into which functions need to be optimized, or, you know, which data needs to be distributed better. And then once that's working, then you can go ahead and scale the input back up and run on the hardware again.
Sounds great, Eric. Thanks, and happy coding.
Thank you. Hope this will be helpful.